quite a few questions that I really want to get through, because then I'll probably be able to take my final tonight.
Okay.
So the first is just, I know logarithms, but every time I get reintroduced to it, I draw a blank. So let's do some logarithm problems. So log 5.
Hold on.
5.
Tell me what the logarithmic expression of that is. That's an exponential expression. What's
Right.
the logarithmic expression?
So let me write that down. Y equals bx.
You don't know this
So
by memory. That's the problem. You need to memorize this. This is the most important thing in logs, is being able to convert between an exponential expression and a logarithmic. There is an equivalent logarithmic expression. What is it?
If I believe it's log x.
Nope. Here's the thing you have to remember. There's only one thing you have to know. Logs are exponents. So if logs are exponents, then on the other side of the equal sign has to be the exponent.
Log equals x.
Well, where's the b and the y go?
So log sub b, right?
Yep.
Log sub b
Of
y.
There you go. You've got to be able to go back and forth between these two. That's a minimum. Okay, now let me give you an example. A equals 2 cubed. There's the exponential. Give me the logarithmic.
Okay, so log sub 2 of 8 equals 3.
Good. And now go back the other way. Hold on a second. Put that logarithmic back into exponential.
I'm sorry. 8.
Nope. Here's the way I memorize it. This works for me pretty good. It's the number on the far left raised to the power of the number on the far right equals the number in the middle.
Right, so 8 equals...
I apologize. Yeah, see, I always write it like this.
Oh.
In other words, I always start left to right. I start with the number on the far left. Now, that may not even be the best memory device to use because sometimes you get this. In other words, sometimes you get this. And then my little thing doesn't work. But if you always remember that logs are exponents, then you know that that number has to be the exponent. And once you figure that out, you can usually work the rest of it out.
Okay.
So there's the key thing to know about logs. There's a few other key things that you also have to memorize, but let's have a look at your problems.
All right, so this says evaluate each expression.
Okay.
So log 5 of 5.
Now, when you're evaluating these, I have found that it's much easier if you go ahead and add a variable. Let's make that equal to x.
Okay.
And now convert it to exponential expression.
Okay, so 5 equals...
5 to what? The number on the far left raised to the power of the number on the far right.
Right, well, I was saying, but like, because...
You're going the other way again. My apologies.
Right.
My apologies.
I'm only doing that because of the formula.
That's fine with me. It was coincidental that these were both the same number, so I didn't know that that's what you were doing.
Okay, so 5 equals 5 to the x.
Okay, now what's x got to be?
1.
That's how you solve that.
Okay, yeah, that's...
It turns out that the log base b of b is always equal to 1, no matter what b is. In other words, if I have the log base 17 of 17, that's got to be 1. Why? Because 17 to the 1 power equals 17.
Gotcha.
All right.
So log sub 2 of 1/32.
Okay, let's go ahead and add the x, just because it completes our method of doing this.
Okay, so 1/32 equals 2 to the x.
Okay, what does x have to be?
X has to be...
Yeah, most of these you can now do kind of manually. Hopefully, because there's no real way to do it out of your calculator.
But what do you put 2 to that it would give you 32?
Okay, let's talk about negative exponents. What does this mean?
That means... Oh, okay, yeah. That means 1/8.
Okay.
So then it would be 8, 16. So it would be -4.
Negative 5.
-5.
One minute, Max. Hello? Yes.
Mom, read this example. This is the direction. Read this example. This is a
I am Max, and I'm currently in a session. Can I call you back? It'll be about an hour and a half, maybe 2 hours. Okay. Thanks. Bye-bye. That's odd.
What?
His name was Max also.
Oh.
All right. What do we got next?
Give me one sec. 12, 13, 14. So I'm just writing down the questions I need help with.
The secret to those log expressions is convert it to an exponential. Always.
Yeah, that definitely makes sense.
Okay. Because then you can solve it without a calculator. If they say, what's the log base 7 of 12? Well, you can't solve that without a calculator.
Right.
So it kind of depends on the problem. But the ones that you can convert to an exponential and solve, that's the way you need to do it.
Okay. So this says rewrite as a logarithmic equation.
Okay.
So it's 3 to the 4th equals 81.
Give me the logarithmic representation of that.
So it'd be log 3.
Base 3.
Log base 3 of 81 equals 4.
Yeah. Notice the log is equal to the exponent. That's why once you figure that out, you're never going to make a mistake here, because that's the base. And the base always goes down here.
Right.
Okay.
That makes sense. So graph the function. Now you have to graph a logarithm. Graph the function log base 4 of x minus 3 plus 1.
Excuse me, hold on. Log base 4 of x minus 3 plus 1.
So I know that's just a...
Well, always start with the parent function. What is the parent function?
Log base 4.
Of x.
Log of x.
No, I mean you need a y and an x in a function.
Right.
Okay. Now let's graph that. Well, log functions are a bit like exponential functions. They all tend to look alike.
Okay.
I can't tell the difference between log base 4 of x and log base 14 of x. For one thing, they all go through that same point, which is 1, 0. Notice that when I make x1, the log of 1 is always 0, no matter what the base. That's another good thing to remember. The log base b of 1 is always 0. Why?
So,
Because b to the 0th power is always 1. Any number to the 0th power is 1.
so no matter what the function is, it always goes through 1, 0?
No, no matter what the base is. Not
Okay.
no matter what the function is. Because let's say I add a plus 2 to that, then it raises the whole thing up 2.
Okay, I got you.
So it wouldn't go through that same point. But that's the parent function. All parent functions go through that point, regardless of the base.
Okay.
It can be natural log, which is base e.
Right.
Be common log, which is base 10. It can be log base 17, and it would still go through the point 1, 0, and it would have this shape. In other words, if I were to just draw this shape, you would not be able to tell what the base was.
Okay.
Okay? So, now, if that's our parent function, we've got two different things that are transforming it. Let's go left to right. What does this 3 do?
It moves it to the right 3 units.
Okay, so I'm going to take that point that I know, and I'm going to move it over here. What's the coordinates on that point?
4, 0.
Okay, and then I'm going to graph it, and notice that my original function actually had a vertical asymptote at x equals 0.
Okay.
So this one also has a vertical asymptote at where?
At x equals 3.
Yeah. Okay, now the other thing that's being done is the plus 1. What does that do?
That lifts it up 1, raises it.
So now I take this point,
So it's 4, 1.
correct? It doesn't change the vertical asymptote because it is a vertical shift.
Right.
So it does not only horizontal changes change that asymptote. So as all I've got to do is graph the same curve, asymptotic with that asymptote, and move it up 1 above the red curve.
But now it's telling me I have to place 2 points. So how do I find another point on the...
Well, okay. How would you find another point? In other words, the point we have is x equal 4, y equal 1. So that's the point we have.
Right.
So let's figure out another point. Pick another x that's not 4.
2.
Here's the problem with 2, is it leaves you with a negative argument. Not only can your argument, this is the argument, not only can your argument not be negative, it can't even be 0.
Okay, so it has to be
That's
above...
the domain. That produces imaginary numbers. So pick a number that doesn't produce imaginary numbers.
5.
We don't happen to know what the log of 2 base 4 is. What do I know? Excuse me, hold on. Don't I know what log base 4 of 4? Oh, that's what we got. Hold on a second. Let's see. That's 4, 1. Why is that 4, 1? The log of 1 is 0 plus 1. Okay, that's 1. So we need this term to be 1. What value of x is going to make that term 1?
4, if it's 4.
No, 7.
No, if... Oh, because so that I can subtract the 4.
Right. In other words, the log base 4 of 4 is 1. So
Right.
if I want a nice, easy number that I don't have to look up in a calculator, then I'm going to choose an x of 7, which gives me a function value of what?
1,
What's the log
right?
base 4 of 4?
Log base 4 of 4 is, it's
1.
not 1?
But then
That's
I'm
what, yeah.
adding 1 to it.
Oh, so it's 2.
Okay, there's the second point. So if I go over here on my green curve and I've got 1 point, which is 4 comma 1. Well, another point would be 7
comma 2.
comma 2. Exactly.
Okay, and so the domain of that is everything greater than 3.
Perfect. Not 3, but everything greater than 3. The domain is x has to be greater than 3.
And the range is infinite.
All real numbers, because it goes from negative infinity, and despite the fact that looks like it kind of goes to a horizontal asymptote, it doesn't. It keeps going
Okay.
all the way up to positive infinity on the y-axis.
Okay. All right, so I get that. Now the next one is use the properties of logarithms to expand the following expression.
Okay, let's go through the 3 properties of logarithms. Property number 1. What's that equal to? That's what it's equal to.
Okay.
If I have the log of 2 times 3, it's equal to the log of 2 plus the log of 3. Which
Okay.
would mean that the log of 6 is equal to the log of 2 plus the log of 3. True statement. Okay?
Okay.
So, entire principle that slide rules were based on. Because then, all they had to do was add 2 things. So they had one of the slides that was a log slide. The other one is a log slide, and if you wanted to multiply 2 numbers together, you just put the 2 slides next to one another, and you got the result.
Okay. And so this one you just would subtract a from b. Log a minus log b.
The thing to remember is you're never doing the same thing as the argument is doing. If the argument is multiplying, you are adding. If
Okay.
the argument is dividing, you are subtracting. And finally, the third rule is the log of a to the b power, which is exponentiating, is b times the log of a. Again, you're doing multiplication one level less than exponentiation. In the first rule, you're doing addition one level less than multiplication. In the second rule, you're doing subtraction one level less than division. And in the third rule, you're doing multiplication, which is one level less than exponentiation.
Okay.
That's the way to remember it. Because the only mistake that people are going to make is saying that that's the log of a times the log of b.
Okay.
That would be doing the same thing to the argument as you do to the separated log statements. That can't be correct. Okay?
Okay.
Now, I'm going to scroll down so you're not looking at those. Give me your problems.
So the problem is log of the square root of the fraction y times z to the 5th over x to the 3rd.
Like that.
Yes.
Okay? Well, the very first thing to do is to recognize that radical signs don't work very good in doing these.
Okay.
Okay? In fact, same thing applies to calculus. Radical signs don't work very good in calculus. Everything's based on the exponent. So let's change this to have an exponential instead of a radical sign. That's always the first thing to do. We're going to base everything on our exponent. What's the exponent need to be? No, square root means what as an exponent?
Square root means 1/2.
Okay, that's what our exponent needs to be. Those two expressions at the top are the same. Now, let's apply the third rule of exponents. What can I do with that 1/2?
Sorry, I'm just writing what you wrote down.
Hold on, I'm not sure that's the first step I want to take. I don't. I want to take a different first step. Always want to work backwards from 3 to 1.
You always want to work backwards from 3 to 1?
You have your 3 rules of logs, right?
Yeah, so log A of B.
So my first step here, and no, you don't always want to work backwards. I don't mean to confuse you.
I thought you'd want to use the first rule.
The better way to look at that is let's go ahead and apply that 1/2 to all the terms inside the argument. What does that give me?
That gives you log times
Log of, not times.
log of.
Same thing as f of x notation. It's not f times x. It's f of x.
Okay. So of square root of x.
Hold on.
I mean square root of y. Sorry, I wrote it wrong.
I use the radical sign. Let's make that an exponent.
Okay, so yeah, so log of y to the 1/2
times z to the
times z to the third
5/2. So all I'm doing is multiplying that exponent times that exponent.
Okay.
In other words,
Over.
When you have double exponentiation, you're multiplying exponents. Over what?
Over x to the 3/2.
3/2. Okay. Now, that being my first step, now let's use rules 1 and 2. In other words, let's separate these into 3 log functions. We're going to have the log of the first function, which is this. And then what's going to come next? Because y is multiplying z. So what do I need next? A plus sign. I'm adding the log.
Oh, right. Okay.
The next thing is going to be what?
Y to the 1/2 plus
Y.
log.
Not y. Y is multiplying z.
No, yeah, that's what I'm just. I was writing down what you were.
I'm sorry. Okay.
Log z to the 5/2.
Right, and then we're dividing the argument by x to the 3/2. So what does that translate to?
Minus log x to the 3/2.
Okay. Now we want to apply the third rule. We haven't fully expanded it yet. But if I apply the third rule, I do. And that's why I wanted to multiply these exponents before as the first step.
Okay.
Because we have a different exponent with each term. So our leading coefficient is going to be different with each term.
Okay.
So using rule 3, what does this first term become?
The first term becomes.
Just bring that exponent down, put it on the algebra line.
So 1/2 times log of y.
Okay, about the second term.
Plus 5/2 times log of z minus 3/2 times log of x.
Yeah. And notice why it would have been a little more difficult if I'd have moved. I could have moved the half down there in the first place.
Okay.
But then I would have had 1/2 in front of my log, and I would have had y z to the 5th. I would have still had to apply that 1/2 to each of the 3 log expressions. And to me, it made more sense to multiply exponents together first, and the very last step is where you use Rule 3. In other words, where you bring the exponent down in front of the log expression.
And so that's fully expanded.
It's fully expanded. Now, make sure.
No, wait, is that log sub y, like log base y, or log of y?
No, the fact that they did not give a b means it's log base 10.
Okay.
And these rules only work if it's the same base.
Right. Yeah, I knew that.
Hold on a second. What the heck? How come I can't go back to my 3 rules? I had it for a second. Oh, there it is. Oh, there we go. All right. Those 3 rules, it's as equally necessary to be able to go from right to left as it is from left to right. You will always get an equal number of questions on any test. One of the questions might say, expand the following 3 log expressions. If you get that question, guaranteed you're going to get another question saying, condense the 3 following log expressions.
Okay.
So it's just as necessary to be able to go from right to left as it is left to right. There's no preference. They're both equally valid.
Right, because there's a next question where it wants me to do the opposite, but I feel like I can handle that, and I have more important things I want to ask you about. So,
all right, I'll leave that.
If we have time at the end, we'll do it.
Okay.
So can you show me the change base formula?
Yeah, that's pretty easy. Log of 7 base 5 is the log of the upper number, not the bigger number, the upper number, divided by the log of the lower number. That being higher up, 5 being lower down.
So
it does not matter what base. Believe it or not, these ratios are all the same. Also, it could be log base 27 of 7 divided by log base 27 of 5. In other words, the base is immaterial. These ratios, the common log of 7 divided by the common log of 5 equals that one. That's the way logs work.
So your answer would be like an actual physical,
No,
would it be log of?
depends. If the teacher says they want exact answers, this is it.
It says round your answer to the nearest thousandth.
Okay, then you need to go in your calculator, get a number, and round it to the nearest thousandth. But know this, you're giving an approximate answer if you do that.
Right.
The only exact answer, and I mean the only exact answer, is this that I've circled on the left.
Okay.
That is a specific exact number. Once you start, these are all irrational numbers. They're like pi and e and square root of 2. The moment you turn it into a decimal, you are approximating it. You're no longer giving an exact answer.
Gotcha.
Go ahead.
But then
make sure you do that in your calculator.
Okay, so log 9.
No, I think it's
No.
7.
Yeah, mine was.
What was your problem?
Log base 5 of 9.
Okay. Got one of them right, didn't I? So your calculator is what kind?
They give me like a little in-between calculator that I have. I'm not allowed to use my own.
Do you have
certain questions allow different things?
You must have 2 log keys on it. You must have a common log and a natural log.
Yeah.
Okay. Use the common log key here. In other words, if they do not specify a base, which I did not, it's base 10. It's also I didn't have to use common log. I actually prefer natural log. Natural log is the log of calculus. Once you get to calculus, you use natural log 95% of the time.
Okay.
So natural log is what I almost always use, whether I'm solving an equation or not. Sometimes you have to solve an equation by taking the log of both sides. I use natural log always.
Okay. And so thousandth is 3 decimal places, right? I'm not.
Yeah, what'd you get? Give me it out to 4.
1.3652.
So that rounds to that.
Okay.
If that was a 5, it would go up to 6.
Gotcha. All right, so next, this is 81 equals 27 to the negative x minus 1 power.
Like that?
Yeah, there's no parentheses.
No parentheses. It matters,
Yeah.
Notice
Yeah.
it matters. When I added
Because
the
that would have turned
parentheses,
it
that would
positive.
have turned it into minus x plus 1.
Right.
That's a different function. Okay? Now, even though we're talking about logs, and most of the time when you have to solve an exponential equation, this is an exponential equation, incidentally. It's not an algebraic one.
Okay.
You cannot solve exponential equations algebraically. Can't do it. If I say 7 equals 3 to the x, there is no way on God's earth you're going to be able to solve that unless you use logarithms. Then you would convert it to logs, and you would have the log base 3 of 7 equals x. Well, the log base 3 of 7 is a number that you can get out of your calculator. So once you understand logs, you can solve this one at the bottom. Now, every now and then you run into an equation like an exponential equation where you don't have to use logs. If there is a common base between that number and that number, I don't have to use logs. Is there?
9.
Not 9. I got to be able to write both of these numbers exponentially. When I said a common base, I meant a common exponential base, not a factor.
Oh, 3.
Correct. And I can write 81 as 3 to the 4th and always use parentheses. Always.
Okay.
How can I write 27?
3 to the 3rd.
The reason you always need to use parentheses is because this whole thing is being taken to that exponent. Now use the rules of exponents. What's the right side equal to? You've got double exponentiation going on. You multiply the exponents.
Okay, so it's 3 to the negative.
Not to the, you multiply the exponent. You're going to multiply that by that. You're not still exponentiating. When you use the rules of exponents, remember, you never do with the exponents what is being done with the underlying function.
Okay.
Always do one level less. Well, if I'm doing double exponentiation here, I'm going to do multiplication. So it's minus 3x minus 3. That's the new exponent.
Okay.
Now, I got same base to one exponent equals same base to a different exponent. What can I do with those exponents?
You can add them?
Equate them.
Equate.
In other words, they have to be the same, right?
Oh.
I can't have, if I have 3 to 1 power equals 3 to a different power, then those powers got to be the same.
Gotcha.
And then I just got to solve that. And I'm trusting you can solve that easily.
Yeah, it's negative 7 over 3.
7/3, yes. Okay, so this problem I was able to do without logs, okay? But it's all I got to do is change one number just a hair. If I make that 80, now there is no common exponential base. I cannot solve it with that method. And I got to use logs.
So how do you do that?
Well,
Here, like this.
I would take the
this
logs
next.
of both sides. Let's just do it with this one. I would take the logs of both sides, and now that allows me to bring that exponent down in front. So I end up with natural log of 80 equals minus x minus 1 times natural log of 27. Well, these logs are just numbers. So now I get minus x minus 1 equals natural log of 80 divided by natural log of 27. Gets rid of that. Add 1 to both sides, so I get plus 1 equals minus x. Divide both sides by a negative. That's what x is equal to. That's how you do it. If you have to use logs, the first step is to take the log of both sides.
And it does not matter which log you use because it's canceling out anyway.
It's not that they're canceling out, it's that you're going to look it up in a calculator anyway. In other words, that answer was a calculator answer. There's no way I can come up with that number without a calculator or a table.
Okay.
So, yeah, it doesn't matter whether I'm using common logs or natural logs.
All right. Equals 4.
Now,
so
I was going to say something else. I forgot what it was. Go ahead and give me your problem.
This is log of, no, sorry. It's 11 to the y plus 3 equals 4.
Notice this is an exponential equation because our variable's in the exponent. That's what it means. And there's no common exponential base between 11 and 4. I cannot write 11 as a power of 2 or 4.
Right.
So I got to use logs to solve this. It's my first step.
You set it to log of 11.
No, you don't set it to. The most fundamental principle of all of algebra is whatever you do to one side you can do to the other and you haven't changed anything.
Right.
And I mean anything. You can square the left side, square the right side, you can square root the left side, you can differentiate the left side, differentiate the right, you can integrate, you can take the logs of both sides. Well, let's take the natural log of both sides. Since we know you have a key on your calculator that has that. Well, I'll get back to a second way to do this in a second, but I'm going to show you it's not any quicker, even though it may be what the teacher showed you. What's the next step?
The next step after that is moving the y plus 3 to multiply by the natural log.
Okay. And what's the next step?
Divide by natural log of 11.
And what's the final step?
Minus 3.
There's your answer. And I mean that exactly, unless your teacher is someone who still wants you to give a decimal answer, which I'm disappointed if he does.
Well, it's not really him. It's an online college course.
Okay. So they want
specific things
turned into a decimal. Okay. Well, go ahead and do it. I don't dispute that. It's
negative 2.42.
Okay. But in terms of math, if you want the most exact answer, this is the only way to give it.
Okay.
No substitute even. Okay. Now, let's go back a second.
Okay.
And instead of taking the natural log of both sides, some clever person says, well, what if we took the log base 4 of both sides? Wouldn't that be easier? What's the right side become immediately?
1.
Does seem easier. I can still bring down the y plus 3 multiplied by log base 4. Now I'm still going to divide both sides by log base 4 of 11.
What you can't do on a regular calculator.
Well, exactly, which means that you're going to have to use the change of base formula, and it's going to involve an extra step or two. So what appears that you saved a step by using log base 4, you didn't really at all, especially if you have to convert it to a decimal.
Right.
In other words, if you could leave that as an answer, then you do save a step.
Okay.
But you can't. And that maybe is one of the advantages of forcing you to convert it to a decimal, is that it teaches you that these apparent shortcuts aren't shortcuts at all.
Right.
Same number of steps, only you got this log base 4, which isn't on anybody's calculator, so better to use either common log or natural log whenever you take the log of both sides.
Okay.
Don't let anybody convince you that it's faster to take the log of the number you're taking the log of.
So now this is solve a system of equations.
Okay.
But for some reason I can't figure it out. So it's negative 2x minus 9y equals 23. And negative 9x minus 5y equals negative 3.
Okay. Both of these are in standard format. Standard format being where your first term's x, your second term's y, and the numbers on the other side.
Okay.
Okay? When that is the case, when you have a system of equations, the best thing to do almost always is to use elimination, not substitution.
Okay.
Okay? Now, elimination requires us to eliminate one of the variables as the first step. Well, the rules of equations say that I can add or subtract any equations, but if I add these two equations, nothing gets eliminated.
Right.
But the other rules say that I can multiply either side by any number I want.
Right.
So what's a common denominator that I can multiply the top equation by and the different number for the bottom equation, giving me the same coefficients for one of these variables? And it doesn't matter whether I eliminate x or y.
I don't know.
How about we multiply the top by 9, and we multiply the bottom by 2. And we can do that well, I can do that as long as I multiply both sides of the equation by those numbers.
Okay.
With me?
Yes.
Okay. So now the new equation 1 is minus 18x minus 81y equals 207. And the new equation 2 is minus 18x minus 10y equals minus 6. Now we got the same coefficients in front of the x term.
Okay.
That means if I subtract these two equations, x is going to go away.
Right.
Well, most people are a lot more comfortable with addition than they are subtraction. In fact, I would venture to say that you'll make half the mistakes if you always are dealing with positive numbers as opposed to negative numbers.
Okay.
So I'd rather set this problem up to where I'm adding the two equations, not subtracting them. At this point, I got to subtract one from the other in order to eliminate the x. Well, I'd rather this bottom term have a plus x coefficient. Well, I can do that by just, instead of multiplying it by 2, let's multiply it by minus 2.
Okay.
With me?
Yeah, so then everything turns Positive.
Well, everything doesn't turn positive. That wasn't the purpose. The purpose is to make it so that I can add the two equations, not have to subtract them.
Right.
And the only thing I needed was for the signs to be opposite on the term that I'm trying to eliminate.
Okay. So then you got negative 71y equals 206.
In other words,
207.
right. Now I get to add these, and adding, like I said, always results in fewer mistakes.
Oh no, you get 213.
Which makes y equal to negative 2, 3. 213 is perfectly divisible by 71. Okay, now we're not done. Because all we did was solve for y. Got to go back to one of the original equations, and that's always the more simple equation. In other words, we've solved for y equals minus 3.
Okay.
Now we got to still solve for x. They said solve for the system of equations, did they not?
They did.
Well, it's never going to be right to use one of these more complicated ones down here because they're bigger numbers.
Right, so we could just use number 2.
Pick the simplest one you can find, and you're right. Number 2 has the smallest numbers. That's usually the simplest one. So I get minus 9x minus 5 times minus 3, and this is the way you want to do it, always. Just substitute before you try to simplify.
Wait, why was it minus 3?
Well, because that's what y came out to be. Remember?
Oh, right, because 71 was negative.
Right. Okay. So the very first step should always be that, nothing beyond that. You don't want to do the biggest mistake I see a lot of my students, especially the smarter ones, and you're definitely a smarter student, but the biggest mistake I see them do is they'll do an equation and they'll do 2 steps in one right there, but they won't do 2 steps in one anywhere else. And then they end up with a mistake. So this process I think is extremely important. Just substitute. Now simplify. Now what do you get?
You get negative 9x plus 15 equals negative 3.
Now what?
Subtract 15 from both sides, you get negative 9x equals negative 18. So x equals 2.
There's the other solution. Now, if your life depended on it, you could go back and you could check and make sure both of those solutions work in both equations. If my life depended on it, I would do that.
Okay.
If you're taking a speed test where you're being timed, well then you shouldn't do that.
Okay.
Okay? It kind of depends on how much confidence you have in your method that you did it right. Maybe it would be worth plugging those 2 solutions into at least one of the equations to make sure that it works. I might do that if I had a few extra minutes, because if you made a mathematical mistake, it'll show up.
Right.
You just plug it into one of the equations. You don't need, like I said, if you wanted to be 100% certain, you'd plug it into both equations, both solutions into both equations, and see that they remain equations. But
all right. So next is graphing a parabola.
okay.
So the equation is y equals negative quantity x minus 2 raised to the second minus 6.
Okay. We're supposed to graph this?
Yeah, we have to graph that.
What's the parent function? Always start with the parent function and treat this as a transformation problem.
Y equals x squared.
You wouldn't have to do that. technically, you could just pick a bunch of values for x, figure out what y is, have a table of x, y values, plot the dots, and draw a line between the dots that looks like a parabola.
Right.
Okay, so you could always do it that way, but that's
what it wants me to do, because it just wants me to plot the vertex and 4 additional points, and it graphs it for me.
Well, that's not what it wants you to do, believe it or not. At least I don't think so. First of all, you're looking at the vertex. What's the vertex?
I don't know. Is that -6?
That number is the x, that number is the y. In other words, this is in vertex format. They gave it to you in vertex format.
So it's 2 minus 6?
Yeah, vertex,
2 comma -6?
vertex format is the following. X minus h quantity squared plus k. So in this case, h is the x coordinate of the vertex, k is the y coordinate of the vertex. So the vertex has got to be at +2, -6.
Okay.
So that goes a long way in plotting it.
Right.
Well, let's see. That is right here. Hold on a second. Let me draw this a little higher up. I need higher up. Vertex is at 2, -6. I will call that point. Now, does this thing open up or open down?
Down.
Okay. Which means there aren't not going to be any x-intercepts. Never going to cross the x-axis.
Okay.
Another thing that means is this has nothing but complex solutions. There's no real solutions to this equation. You will not find a value of x that lets y be 0, because it never crosses the x-axis, so that when you're on the x-axis, y is 0. So the most important point besides the vertex at this point is that point right there.
Okay.
What is that point?
That's the y-intercept.
Which is when x is 0. So
Right.
plug in x for 0 and tell me what the y-intercept is.
0 minus 2 squared minus 6 y equals -10.
Okay, so that comma is 0, -10 is that point. Now that allows me to solve for that point pretty easily, because it's symmetrical. Everything is symmetrical about that line of symmetry.
So it's 2 negative...
It's not.
Oh, no, it's 4 -10.
You got it. 4 -10. So now we have 3 points. Now that's all any teacher should ask for, because 3 points determine a parabola, not 5. You don't need 5. It's like 2 points determine a straight line. Well,
Right. You want 5, though.
3 points determine a parabola. Okay, well we got 3. Is all you got to do is pick one more value for x that's not 2 and not 0 and not 4.
So let's do 1.
Okay. What's y equal to? What's y of 1 equal to?
1 minus 6. Y equals -7.
Okay. Which means that when x is 1,
Y is -7.
y is -7.
And when x
This
is...
point. What is that point? The symmetrical point.
3,
Comma -7.
comma, -7.
There's your 5 points.
Okay.
And you can always get 5 points by just plugging in 5 numbers for x. In other words, I didn't really have to do it this way. I did it kind of the most efficient way, which was to use symmetry to come up with these points on the right. But you wouldn't have to do that. You could let x equal 0, x equal 1, x equal 2, x equal 3, x equal 4, x equal 5. That's going to give you 5 points.
Okay.
Okay? Although the vertex is one of them, so you only need 4 other values of x.
Right. Okay, so
notice that I could have graphed that as a transformation of a parabola, knowing that first of all it was reflected over the x-axis, and then knowing that it was shifted horizontally by 2, which you can see, and then knowing that it was shifted down by 6. So if I start with my parent function and I do those 3 transformations, I get this graph that we drew. Although it doesn't give you the points, but it does allow you to graph it.
okay. All right, so then it gives me quadratic equation negative 3x squared plus 30x minus 72. And it asks me, so the equation for finding,
Is that equal to 0 or not?
it says it's equal to g of x.
Okay. In other words, do we have an equation or do we have an expression? What we have is an expression. Okay.
And so it says, does the function have a minimum or maximum? It has a maximum because it opens downwards.
Okay.
It says, where does the minimum or maximum occur? And I found this formula that was, let me find it.
What they want is the g of x value. No, what they want is the x value, where it occurs, and the g of x value would be what would it be? So there's 2 different questions here. It's where it occurs on the x-axis, and what is its g of x value when it's at that value.
Right. And I found a formula that gives you x, which is where it occurs.
Minus b over 2a.
Yeah.
Okay, that's the easy one. You always want to remember this one. Plug it
minus b over 2a, which is...
You don't need the other one, incidentally. In fact,
negative...
I would almost suggest you do not memorize what the y is.
No, because you could just plug in the x.
Exactly. And the y is a very complicated one. So,
yeah, so I don't want that.
There's no point in memorizing it. It's easier to take whatever value you come up with and plug it into the function.
You
figure out what g of x would be. So what's minus b over 2a?
Negative 30 over negative 6.
There's 5. So that point,
yes, that's what I got.
5.
And then it told me to plug in the x's for 0 to find the function's minimum or maximum value.
Hold on. Said what?
I found online that it said to plug in all the x's as 0 to find the function's minimum or maximum value.
Well, that's not quite true. If you plug in x equals 0, what you're going to find is this y-intercept.
So you have to plug in the 5.
But if I plug in 5, I'm going to get what they're looking for, which is the maximum value, which is g of 5. Okay, so I'm going to write it like that. Now plug it in.
All right. Negative 3 times 5
squared
plus 30 times 5 minus 72.
Okay, now let's come up with a number for that.
So negative 75 plus 150 minus 72.
3.
3?
Uh-huh. That's what that number is. I got it because minus 75 and minus 75 would be 150. And we're 3 less than minus 75 over there. So I got to end up with a positive 3. That's
All
what the maximum value is. It occurs when x is equal to 5.
right. Okay. So
Did you
next.
want anything else on that
No,
problem?
that was it.
Okay. Yeah. Yeah. What you looked up on the internet actually sounds like it might apply to calculus, where you
Or the y-intercept.
well, you have functions that are greater than the cubic functions, for instance. In other words, if I have a cubic function, then the function might look like this. Well, now there's a maximum value there and there's a minimum value there as long as we're within a domain like that.
Oh.
So when you get to calculus, that's the kind of answer you got when you looked it up. Is an answer that applies more to calculus than it does quadratics. Quadratics only have one maximum or one minimum. There are not more than one place on that thing because they're all parabolas.
Okay. I'm going to send you an email really quick.
Okay. While you're doing that, I'm going to go down and turn my oven on. Excuse me 1 minute. I'll be back in 60 seconds. Okay. I did not get your email. There it is. Actually, it's nice when you send me a screenshot because then I can immediately take a screenshot of it. It's filling up my whole screen and then I can write on it. So. That function, what kind of shape is that?
It's a parabola.
Opening up or down?
Up.
So it's like that. Maybe crosses the x-axis. We'll pretend it crosses the x-axis. Probably does. Like that. They want to know where that occurs. By that I mean the minimum value. So whenever you have a function that is a quadratic, there are a couple of key questions, and that is where does the minimum occur or where does the maximum occur? That's all.
So I could just use the formula immediately.
It's always what you're curious about. Yeah, because that's where that's how many you're going to produce. In other words, whatever x comes out to be, that minimizes your cost. That's what you generally want to do. Or if you had a profit function, you'd want to maximize your profit. That would be a parabola pointing downwards, and the key would be to find the x value that produces that maximum or minimum. So this x equals minus b over 2a is a really good one to memorize.
All right, and in this case, it's 2,000.
So x equals 2,000?
Yes.
So that's 2k right there. And that's all they wanted. Oh no, what is the minimum unit cost? So,
all right, so I plugged 2,000 in.
When 2,000 machines are made, that's when you get your minimum cost. And what is C of 2,000 equal to?
Okay, give me 1 second. So plus 22 21. So I'm just going to do this on my calculator. Times point.
Do not round your answer. That's interesting. What does that mean? What'd you get? I'm curious.
I'm working on it.
Okay.
120 times.
I hate it when they do this, when they give you all these big complex numbers. Just takes time, wastes time, and doesn't enhance the understanding one bit. It's just a real type problem. In other words, this is a real world problem. So
Right.
they use real world numbers, which is okay, I guess.
So I got 982,181.
Nice round number, no decimals.
No decimals.
That's the minimum unit cost? Something,
Yeah.
something doesn't sound right. So you're telling me it's $982,000 to produce a copy machine? I doubt it. When you get an answer that does not seem like it could be real, it usually is indicative that you've made a mistake somewhere.
Right, but
It might be the 2000 that's the mistake. I don't know. I didn't check. You want me to check real quick?
I mean, I guess.
Okay, minus B is 120 divided by 2 times A, which is 0.6.
Oh, I did make a mistake. I put .006.
That's 200.
200, not 2,000.
Okay, now that's going to make a difference. I'm not sure how many. I think you got to do the whole thing over again. I don't think I can figure out what the answer is just by knowing that it's
No, I'll do it really quick.
0.
Minus 120 times 200, just 24,000 plus 22, 181. So 24. It's 10,181.
That makes a lot more sense.
Still pretty expensive.
Still, it illustrates a very important point of math. Always be aware of what your ballpark should be. If I came up with 10 million, well, you know that can't be right. Copy machines don't cost 10 million.
Right.
Okay?
Do copy machines cost 10,000?
Yeah. Some of them,
Okay.
might. If they're really exotic ones, yes. I mean, perhaps. I don't know. I didn't check your answer, so I don't know if that's right or wrong. But I did check X, and X of 200 makes a certain amount of sense.
Okay.
In other words, you save, your cost gets minimized. If you're just making one copy machine, then all your fixed costs are high. You got to pay rent, you got to pay power. So it figures that your minimum cost per unit is going to be smaller if you make more of them, but not necessarily if I make 10,000 of them. In other words, the minimum cost per unit is achieved when we make 200 units.
Okay.
Once I make 201 units, cost goes up per unit. If I make 199 units, cost goes up per unit. But if I make exactly 200 units, the cost is the minimum it is possible to be per unit. And then you just plug in 200 and figure out what that is. Let's see if 200 is. All right.
Compose. All right. Another email.
Okay.
I think I got the answer to this one, but I just want to double check.
Your email say sent yet?
Yeah.
about a 15-second delay, I think, in between when it says sent on your end and when I get it. Is there more than one function? I'm only seeing one function.
Did my email only have one function in it?
Well, can you see what I'm looking at? Am I not seeing the whole thing? Here, let me go back and look at your email.
It's covered in the black. No, wait, click on it.
Ah, I see it now.
Yeah.
Okay, so the problem is when I download it, that doesn't come through.
No, it did. It was just covered by black. Like, hit it again.
Oh, yeah, you're right. Ah, I've always wanted to know how I get rid of the black top and bottom. Do you know?
I actually don't. Maybe if you... I really don't know. Maybe the 3 dots in the top right?
I hate this. The fact that they cover it up. View actual size.
Yeah, hit that.
No, no, I don't see. Oh, no, I don't see it. But I can get those functions. Just read it to me. What's the first function?
First function is 4 times the quantity...
What's it called? G of x?
F of x. Equals 4 times the quantity x minus 3 to the third.
And this
times the quantity x minus 1.
And this shows...
Now, they taught me a fast way to do this when it's already factored.
Okay.
So 4, and that's first x is to the third, and the second one is to the first. So it's 4 times x to the fourth. And if it's even, if the exponent of x is even, they said that it behaves the same way on both sides. It'll either rise to the right and left or fall to the right and left. And if the leading coefficient is positive, then it will always rise to the right. So.
Okay. Something else here that you need to know. When you have a cubic function like that, it can have at most 2 humps in it. That's got 3 humps. That's got a minimum there, a maximum there, and a minimum there. So graph B cannot go with h of x. Impossible.
Right.
It can only have, these are called local extrema. Okay?
Right.
That's what they're referred to as. And you can only have one less local extrema than the degree of your polynomial. Well, this is 3rd degree, so it can't be B.
Can only have 2.
Yeah, could be C, could be A, could maybe be D. I'll have to scroll up and look at that. But that's an important consideration. So this one, which has 3 extrema, could be this function. Notice that you hit it right on the get-go. That's an x to the 4th. That is a 4th degree polynomial.
Okay.
Okay, so it doesn't have to have 3 extrema, but it usually does. And not seeing all the curves here, so let me scroll up. That's the only function, that's the only curve that we're looking at that has 3 extrema.
Okay.
That's got to be your f of x.
But why? It says that it has to touch or cross at...
Okay. Well, let's talk about more. There's more things here. Hold on. Give me the function again. I'm sorry, I erased it. What is it?
4 times the quantity x minus 3 to the third times the quantity x minus 1.
Let's find the zeros.
3 and 1.
So the zeros are x equal 3 and x equal 1.
How do you tell if it crosses?
Whether the exponent is odd or even.
The leading coefficient exponent.
Not the leading, the exponent. In other words, this 3 and that 1. Remember, that's going to produce an x to the 4th. However, I got it wrong. Our zeros, graph B does not appear to be this.
No.
First of all, I need zeros at 1 and 3, and it's got to cross through the axis at both of them.
So it has to cross through because it's even?
Because it's odd. If
Why?
it's even, it kisses. Notice what, always refer back to equations you're very familiar with. That's y equal x squared, right?
Right, so even touches.
Even touches. Odd.
So, but it doesn't have to do with the leading.
If I got y equal x cubed, it crosses and goes through the x-axis like that.
Okay. So, but it's not the leading one, it's each specific
Nothing
zero.
to do with the leading one. It has to do with the size of the exponent of your zeros.
Okay, the zeros.
In other words, we have a 0 at 3, but we actually have 3 of them. That's a multiplicity of 3.
Okay.
Now, if they haven't taught you about multiplicity...
They have, yeah.
Okay. So, now I need to find a function that's got zeros at 3 and 1, and it crosses at both.
And it has to rise on both sides, so it's A.
Right, so it's probably A. Yeah, there's the one, there's a 0 at 1, there's a 0 at 3. It crosses through on both, and it's open and open. In other words, this is called the end behavior. The end behavior comes when x goes to negative infinity or x goes to positive infinity.
Okay.
And when either of those happen, then y goes to positive infinity. So it's open on both ends.
Okay.
Max, give me another 60 seconds. I'll be right back. Kind of a crazy day. I have like 5 sessions today. I got to squeeze my lunch in when I can. So I'm putting my lunch in. All right, so we figured out that it's probably A. Now, that was a little bit surprising, although it shouldn't have been, because I only see maybe one extrema, that one right there. But just because it's a third degree function, or in this case a fourth degree function, doesn't necessarily mean it has all those extremas. If I look at y equal x cubed, notice I don't have any extrema, and yet I still have a third degree polynomial.
Okay.
So you don't have to have as many extrema, one less than the degree of the polynomial. That's just the maximum you can have.
Yeah, it's just the limit.
You can have more. Right.
Okay.
So the fact that I only see one here doesn't mean it can't be a quartic. And in fact, it is that function. Okay, so now let's look at this function over here. We haven't identified it yet.
Right. So I already factored it and everything.
Okay, what'd you get for the zeros?
So for the zeros, I got -4 and +2. And 1.
So
at 0 itself. Yeah, it's 3 zeros.
Okay.
No, it's not 1, it's 0.
So
Yeah.
-4, 2, and 0. Well, that should be relatively easy to find. 0, 2, and minus 4. Looks like D.
0. The multiplicity of all of them is 1.
Yeah, well, we don't even need that. Oh, yes, we do, because we got a C up here also. In other words, C has the same 3 zeros. So I have to figure out the end behavior. And the multiplicity is the same. In other words, C, you'll notice, is just the reflection of D.
It rises to the left and falls to the right.
Which is correct. When x goes to negative infinity, does y go to positive infinity or negative infinity? That's how you answer it. When x goes to positive infinity, when x goes to negative infinity, it's actually easier if you use positive infinity. First of all, the only term that matters for end behavior is that first term.
Right.
So when x goes to positive infinity, what does h of x go to?
H of x goes to negative infinity.
That means C is correct.
Right.
Not D.
Okay. Okay, so this says graph all the vertical and horizontal asymptotes of a function.
Okay.
So I'll give you the asymptotes. I'll give you the function. So the function is f of x equals 2x minus 11 all over 2x plus 9.
First thing to always consider is vertical asymptotes. Where do vertical asymptotes come?
Vertical asymptotes are the zeros, right? The zeros of the denominator.
Correct. Where's the zero of the denominator? There's only one.
X equals negative 9 over 2.
There's our vertical asymptote. How about a horizontal asymptote? That's next.
What is negative 9 over 2?
That's the vertical asymptote.
So that's the vertical asymptote, which is 4.5.
Uh-huh.
Yeah.
Negative 4.5, right. The longer I'm in mathematics, the more I realize that improper fractions work a lot better than proper fractions.
Yeah.
Always. I'm almost never seen a case where proper fractions is what you need, unless you're out there measuring lumber or something. But if you're doing math, leave it in ratios. Simplify the ratio, but don't convert it to proper fractions. That's almost never correct, yeah.
So then
Horizontal
the horizontal asymptote, that is because the multiplicity of the numerator and denominator's leading coefficient are the same, you divide, right?
Correct.
And you get 1.
If the degree in the numerator of the x is the same as the degree in the denominator, the maximum, then it's the ratio of their coefficients.
Okay.
So it's y equal 1.
And that's it. Okay.
That's it. And what that does is it allows you, it draws the basic grid on there. We know that this function is hyperbolic in nature. That means it basically looks like a hyperbole, like that. Okay? Only it's drawn about our grid. Well, we've got a perfect grid now. There's only 2 ways this function looks. It either looks like this, or possibly it might be in the 2nd and 4th quadrants.
Okay.
I don't really know for sure. How can I determine which it is?
If it's positive?
No? Plug in a value for x and we'll see where it lands up, and then we'll know which one we have. Plug in an easy value for x.
Plug in 0, you get negative 11 over 9.
Okay, a negative 11 over 9. This line right here is at 1. So we must be right here.
Oh, okay.
Okay, I haven't drawn it quite right, but the question is f of x greater than 1 or less than 1? That's all we need to know. If it's less than 1, then it's our red curve. If it's greater than 1, it's our black curves.
Okay, that makes sense.
And I don't know of an easier way of determining that. That's pretty easy. Is to plug in a convenient value for x and figure out which side of those asymptotes you're on.
Okay.
And since that is at 1, I know I'm south of that, so I got to be on my red curve.
Okay. So this next rational function is a graph that I have to graph is f of x equals -4 over x minus 2. So the vertical asymptote is immediately at 2.
Horizontal asymptote?
Yeah.
Where?
Well, it's at, I don't know because they're not the same.
Y equals 0. If the denominator is a higher degree than the numerator, and it is because the numerator is basically x to the 0, and this is x to the 1, so my denominator is a higher power of the variable, which means my horizontal asymptote is always y equals 0.
But what if, I know there's a rule for if it's exactly 1 degree higher.
Then you have to do the division. You're talking about for the denominator or the numerator being 1 degree higher?
The numerator.
If the numerator is 1 degree higher, like you have something like this, you have to do the division. You have to manually divide it, and you'll convert it to something with a remainder, and then you look at the something.
Okay.
That's the only way.
And that's the slope, right?
Well, if the numerator is 1 degree higher than the denominator, and you do the division, you get a slant asymptote, or what's called an oblique asymptote. The only time you get that is if the numerator is exactly 1 degree higher than the denominator. And you always, when you do that division, you get a straight line. So a slant asymptote might look like this. And then that gives you a different grid to draw it in. In other words, now your grid might result in a curve that looks like that when you have a slant asymptote.
Okay.
Okay? But basically on all of these hyperbolic functions, the goal is to get your grid drawn. Once you've got your grid down, your horizontal, your vertical, and your slant, if they exist, asymptotes, then you can draw the hyperbola in there.
Gotcha.
So,
and now it wants me to graph the whole function.
Okay.
The whole.
So we had a vertical asymptote at 2. We had a horizontal asymptote at 0. So we know, again, the curve has to either be this or this. Tell me which.
It is the black because I plugged in 0 and I got 2. So 0, 2 is in the black.
Ooh, is it? There's 0.
0, -2. Sorry, 0, -2.
It's not -2. When you plug in 0 for x, you get +2.
Oh, did I do that wrong? I did that wrong.
Yep. So it's the red.
The red. So it's 0, +2.
When x is equal to f of 0 is +2, well, the only +2 we've got is right there. This would be a negative number if it were the black. So it's not the black. And one clue that I have picked up over the years is that if you have a negative sign, it's usually second and fourth on your grid, not first and third.
Okay.
Although you'll notice the previous problem, there was no negative sign and we were still second and fourth. In this one, there's no negative sign in front. It's 2x minus 11 over 2x plus 9. That still came out second and fourth.
Okay.
So if I were to put a negative sign in there, in front of that whole thing, that would actually switch it to first and third.
Okay.
Okay? So you can't always tell which one it is based on whether there's a negative sign or not. The surefire method is to plug in a value for x and figure out where f of x is, and then that'll tell you immediately which curve it is.
Okay.
Okay? Max, I need to go.
Okay.
When is our next? We have a couple of sessions tomorrow.
Yeah, if I end up taking my final tonight, those will probably be canceled.
Okay. I do have time. If you need another session later this afternoon, I could do it. I'm scheduled right now from 2 to 3:30.
Okay.
And then I've got a 4-hour block after that where I'm available. So if you decide to take your test tonight and you want another session before you take it, you can get back to me at 3:30 my time, which would be 5:30
Which is
your time.
5:30 my time. Okay, we might be able to do I might be able to do like a half hour there.
Okay, whatever you need. And if I don't hear back from you, I will just assume that we're on for tomorrow at 11 and 1.
Okay.
Let me know as soon as you know, because
I will.
see, my day is pretty hectic tomorrow also. I don't know what's going on. My Saturdays and Sundays are usually I'm off. I got nothing. And this weekend I had like 9 appointments. So,
yeah.
All right.
Okay. I'll let you know.
Okay, Max. Good luck to you.
Thank you.
Bye-bye.
Bye.